Hello, good evening, student. Today we will discuss about week 11 assignment and also doubts which are raised in week 11 lectures. Okay, so we will wait for couple of minutes. So more students can join, then we will start. My slides are visible. Hello, am I audible to you? Yeah, my slides are visible, na? Okay, then wait for 2 minutes. Okay, then we will start. Just 4 minutes. Okay, we should start now. So first of all, we will solve question answer of week 11 assignment. Okay, it is a assignment of previous semester. It will help you to solve assignment of ongoing semester. Okay, so let me start. Okay, so question number 1. The electroanalytical method, which is based on measuring current as a function of applied potential. Okay, so it is very simple question because it is already explained very well in lectures that electroanalytical method which measure current. Okay, and this current is what function of applied voltage. Okay, so what we are doing, we will change potential. Okay, and with respect to change of potential, how current will be changed. Okay, so it will be measured and it will be used for analytical purpose. So this technique is known as voltammetry, means volt and ammetry means voltage and ammeter means current. Okay, so we are measuring current as a function of voltage. Okay, so we applied voltage in different fashion. Okay, suppose you are applying voltage, okay, with time. So simplest method is you are applying voltage in linear way. Okay, so linearly means as time is increasing, your voltage is also increasing. Okay, so it is the simple linear way. So there are different way, like you can range potential, okay, pulse wise also, like there are some pulses of each. So this is all about voltammetry. Okay, and we will discuss further in detail in next question. Okay, so this is the explanation of this question. The term voltammetry refer to group of electroanalytical method. Okay, voltammetry itself is very big analytical method, and it cover different type of voltammetrics are there, and different type of with their different applications. Okay, and where many modern techniques are there which are being used in minor as well as in major industrial level. Okay, so it is very important technique with respect of analytical chemistry. Okay, in which acquire information about the analyte, okay, by measuring current in the electrochemical set. Okay, so this all voltammetric, okay, this is because this is electroanalytical technique, so it should be happen in electrochemical set, which we discussed in last class. Okay, or you can say last week, as a function of applied potential. Okay, we obtain this information under condition of promote polarization of small indicator. Okay, so it might be polarization of small indicator which you are reading, or working electrode. Okay, so these are the means if you have you are applying a voltage. So why we are discussing about that, I will give a simple example, okay, which sir also explained. Okay, suppose you are going to measure suppose chloride ion, okay, in your analyte. Okay, so this is your analyte, it contains some amount of chloride ion, okay, some concentrations, let's say C is X, we don't know. Okay, so how we will measure? Okay, so simply you just immerse one electrode. Okay, suppose it is made of Ag. Okay, suppose this is made of, okay, and if you applied a potential where the reaction will be occur like Ag convert in Ag plus electron. Okay, so what is happening here? Oxidation. Okay, oxidation reaction is going on. So when this Ag will be when Ag solid Ag will convert in ionic form, this Ag will be dissolved in the solution. Okay, and it means it will be removed from electrode, you can say, and it will be emerge into solution. But this solution also contains chloride ion, so this Ag plus ion will react with chloride ion, and it will make AgCl precipitate. Okay, and it will be settled down. So finally what happens? If you are continuously increasing the current, okay, still you are giving current here. Okay, so then Ag will be there in solution, but chloride will be not there, because chloride is already consumed. Okay, so chloride is not there, only Ag is there. So due to increasing the Ag, what will happen? The current will be increased, okay, drastically. So if you plot the graph, okay, you will see that as you are plotting graph between E and I and E. Okay, just a minute. Okay, so initially current, only minute current will be flow due to another reason. Okay, but when complete chloride will be consumed by Ag ion, and it will be form AgCl and get precipitate. Okay, after that, when Ag will be increased in the solution, the current will be increased drastically like that. Okay, so at that point you can say that this voltage is my end point. Okay, at that point. Okay, so this method is also known as colorimetry. Okay, so you can measure the how much charge you provide in the electrochemical set. Okay, on the basis of that you can say that means how much chloride ion was there in your analyzer. Okay, so this is a simple example of volumetry, or you can say basic thing, okay, about the volumetry, voltammetry. Okay, so I think one student has his mic on, so please keep your mic muted. Okay, yeah. So this is all about the first question. I think it is clear. Any doubt in this question you can ask. Okay. So question number second. Among the following, the linear scale existing signal is used in case. Okay, what is linear scale first of all? Okay, linear scale means you are going to. I have already explained, but let me explain one more time. Okay, so suppose this is the voltage. Okay, with respect to time. So it is linearly increased. Okay, so what is meaning? If you count it, it will be means volt per second. Okay, so this rate is known as what? This scan rate, you can say. Okay, so this scan rate is constant here, means continuously voltage increasing with respect of time. Okay, so your voltage per second is constant. Okay, that's why you are getting linear graph. Okay, so this is known as a linear scan. Okay, you are scanning, but you are linear scanning, means you are applying voltage in continuous fashion. Okay, so that with respect of time your voltage will be increased. Okay, okay, and it will be help you to measure that a particular reaction is happening at particular voltage. Okay, so or at that point it will give current. Okay, so you will able to measure current at that point. Okay, so like that it is E. Okay, so as you are increasing what say potential. Okay, so at some point the current will be increased. Okay, so this current you can measure that this is the potential where the reaction is happening. Either it is half cell reaction or complete half cell reaction, you can say, either reduction or potential. Okay, so you can measure in this way. So the question is asking that among the following, the linear scan existing signal is used in case of. Okay, so hydrodynamic voltammetry is right answer. Okay, because first of all we will discuss another option. Okay, cyclic voltammetry no, because cyclic voltammetry we know first we will increase the voltage. Okay, then again we scan in opposite side. Okay, so it is not linear scan. Then square wave voltammetry. Okay, so square wave voltammetry is also different. Okay, it is like if you draw the graph, it will be like that. Just a minute, square wave. So it will be okay. It is not clearly. Actually, I need to draw face right now. Just a minute. Okay, so square wave means you are going to increase light. Okay, so if you see, this is the combined graph of linear, means you can say no, not linear, step like that. Okay, means it is addition of two type of graph, this type of graph and this pulsing. So if you add these two type of scan, you will get this square set scan. Okay, so this is also not right option. Then differential pulse polarography. So this is the totally different. Okay, because differential pulse. So what you are going to measure here? So you are going to measure current in a different pulse. Okay, so this is totally. We will discuss about this also. I think it is it need to explain in some question, okay, which will become in further slide. So hydrodynamic voltammetry is diet option. Okay, so let me explain what is the hydrodynamic voltammetry. Okay, so this is the hydro. So can you can understand by this name only what is the hydrodynamic device. Okay, so hydrodynamic. Okay, hydro means generally it is used for water, and dynamic. Okay, so dynamic means moving, something is moving. Okay, so here some your electrolyte is moving or your analyte is moving like that. Okay, so how you can move your electrolyte? Either you can stir this solution or you can rotate your electrode. Okay, so your rotate is your electrode itself is working as a stirrer. Okay, so these are the things which is known as a hydrodynamic device. Use convection to enhance the rate of mass transfer. Okay, why we are doing this, why we rotating our electrode? Because it will increase mass transfer. Okay, and can offer advantage over technique which operate stagnant solution. Okay, other techniques are stagnant. Okay, where your solution remain stagnant. The addition of convection to the cell usually result in increased current and sensitivity in comparison of voltammetric measuring performance stagnant solution. Okay, so these are the advantages where it will increase sensitivity. Okay, and current also, increase current and sensitivity. That's why we are using this hydrodynamic method. Okay, or hydrodynamic voltammetry. Okay, so similarly here, so you can see here it is counter electrode. Okay, it is reference electrode. So these two electrode are, we know. Okay, from where current will be flow. Okay, no, sorry, reference electrode current will be not, only voltage will remain same. It will counter this working electrode and reference electrode. Okay, but counter electrode is different. Okay, so current will be flow in between working electrode and counter electrode. Okay, so this electrode is working electrode which is rotating here. Okay, so this is all about hydrodynamic voltammetry. Question number 3. Question number 3 is match the type of excitation signal given in column A with voltammetric technique given in volume B. Column B, sorry. Okay, so it is I think many things we have already explained. Okay, so a linear scan. Okay, so linear scan is generally done in hydrodynamic voltammetry, and same in polarography also. Okay, so this is right answer. Then differential pulse. Okay, so it is name says differential pulse means it is differential pulse polarography. And triangular means what? This is, it will look like suppose it is voltage and it is time. So you are increasing voltage, then you are decreasing voltage. Okay, so this is means once you are increasing voltage, then you are okay, so here you are increasing voltage at till certain point, then it is decreasing voltage. Okay, so this is it will be make a triangular graph like that. Okay, that's why it is known as a triangular cyclic voltammeter. Okay, so triangular means it is known as a cyclic voltammeter. Why cyclic? Means you are increasing voltage, again decreasing voltage, then again you will increase voltage, then again decrease voltage. Okay, so this cycle will be continue. Okay, that's why it is known as a cyclic voltammeter. Okay, so option you can find out. It is okay. So it is explained here. Linear scan we have already explained with respect to E and time. Okay, it is constantly increased means your scan rate is fixed. Okay, voltage per second, whatever you are increasing, it is fixed. That's why you are getting a straight line. Okay, so polarography means the type of voltammetry which used linear scan type of voltammetry as polarography and hydrodynamic voltammetry. Sorry. Okay. Second is B is differential pulse. Okay, where you can see here what the scan rate is increasing continuously. Okay, but it's after a time interval you are giving a peak. Okay, a peak voltage like that. Then again it is come here, then again one peak is there. Okay, so voltage is increasing. Okay, additionally we are increasing voltage in peaks also. Okay, you are giving some peak voltage with definite time interval. Okay, second, this is the square third is square wave. Okay, square wave means what? See here. Okay, then you give pulse. Okay, then it is not means some voltage it is increased, then again you give pulse. Okay, so pulse, so means after that one pulse voltage increase. Okay, some point, then you give again same pulse, then again voltage increase, like that. Okay, so it is means from here to here time will remain voltage will remain constant for some time. Okay, but here if you see, for this time interval also the voltage is increasing. Okay, so this is the difference between differential pulse and square wave. Then triangular. Okay, it is already explained, E versus time. Okay, so you are increasing voltage at certain point, then it is decreasing. Okay, so it is continuously going on. Okay, so this type of you can say scans which are being used in voltammetry, on the basis of different type of voltammetries are being used. Okay, so this square wave, if you are applied square wave scan, then it is known as a square wave voltammetry. Okay, it is a differential pulse voltammetry, it is a cyclic voltammetry. Okay, so this concept should be remain in your mind. Okay, why this why different type of voltammetry are there. Okay, so it is based on their scan and type of scan. Okay, so 3 questions are clear. Now question number 4. In cyclic voltammetry, the current in cell passes between. Okay, so see, this question is already explained by me now only. The cyclic voltammetry, the current in cell passes between what? Okay, so so what is the arrangement? Okay, if you see, okay, so this is suppose your working electrode, this is your counter electrode. Okay, and suppose it is your reference electrode. Okay, so in between that the voltage will remain constant. Okay, because here I will be, means you can say 0, approximate 0. Okay, not let me. Okay, so we can say here that it is approx 0. Okay, so I is approx 0 here in reference electrode. Okay, so then what will be suppose you are going to connect one battery. Okay, so this is the actually arrangement. Okay, where you can say here you can attach 1 ampere ampere galvanostat, you can say. Okay, galvanometer, so where you will be able to calculate current. Okay, and finally it is cell where electrolyte is filled. Okay, so this is the total arrangement of your cell. Okay, minus and plus. Okay, then see, now what will be the option? Cyclic voltammeter, the current cell passes between working electrode and reference electrode. No. Okay, it is already explained here, because current is approximately 0, so that we can maintain constant potential. Okay, in between working electrode and reference electrode. Okay, then counter electrode and reference electrode. Okay, no, it is a reference electrode, current will never flow. Okay, so these two options are automatically incorrect. Then working electrode and counter electrode. Yes, this is right way, because if you see this circuit, you can say that that circuit is current is flowing between counter electrode and circuit working electrode. Okay, so this is right option. Okay, so current will be flow in between working electrode and counter electrode. Okay, so reaction will be happen at working electrode. Okay, it can be oxidation, reduction. Okay, it's on the basis of your connectivity. Okay, so different type of reaction will occur, and on the basis of these reactions you can measure your error. Okay, Clear this question? Any doubt? Any doubt up to this question? Okay. So this is again explained. In case cyclic voltammetry, three electrodes are required: working electrode, counter electrode, and reference electrode. The working electrode is the electrode at which the analyte is oxide or reduced. Okay, both can be happen. Okay, it is depend on what? It is depend on your analyte, what you are going to analyze. Okay, so it is depend on that. So either it is oxidation or reduction, any reaction can happen. Okay, and on the basis of this reaction only you will able to measure that how much analyte is present in solution. Okay, the potential between the working electrode and reference electrode is controlled. See, this is always even constant. How it is even constant? Because we are not providing current, so current is not flowing. I approximate 0 here. Okay, so that why we are and this thing is also explained why we are using reference electrode. Okay, we are going to protect from IR drop. Okay, because otherwise if you are providing voltage in between counter electrode and working electrode, then there will be some IR drop, okay, of the solution, so that it will drop your potential and whatever. Okay, that's why we are using reference electrode. Okay, electrolysis current passes between the working electrode and counter electrode. Okay, so it is already explained. This is the right answer of this question. Okay, I think it is crystal clear. Any doubt you can ask up to here. Okay. So now question number 5. Question number 5 is, for a simple redox events. Redox means reduction and oxidation. Okay, you can say reversible reaction in simple form. All other factors except scan rate is kept constant. Only we are changing scan rate. Okay, then highest peak current will observed in case of, see, so you are changing only scan rate, and in starting of question it is explained that it is redox event. Okay, redox means suppose it is x, so x is converting a y, giving an electron, or you can say it is x only. No? Okay, so it is x only, and same this reaction is happening. Okay, so it is oxidation and it is reduction. So this is the redox reaction. Okay, so obviously it will be reversible reaction. Okay, so in reversible reaction all other parameters are fixed, kept constant. Okay, so so finally this question is asking that what scan rate should be there. Okay, what scan rate should be there so that this redox reaction can be happen. Okay, if scan rate is higher, then you will not able to maintain this redox reaction. Okay, so this is the maximum, means you can say a permissible limit up to what you can increase your scan rate. Okay, so it is I think 50 volt, 80, okay, sorry, 80. Okay, so it is up to 80 volt per second. Okay, so hence when all the factors except scan rate are constant, the highest peak current will be obtained at highest scan rate 80 volt per second. Okay, so you can increase your scan rate up to 80 volt per second, not beyond that. Okay, so how it is derived? It is derived from this equation, and this equation is known as Rendick-Sovic equation. Okay, Rendick-Sovic equation. Okay, so it is Rendick-Sovic equation where n is how much number of electron transferred in electron. Okay, suppose it is Fe plus 2. Okay, so it is Fe plus 3 plus electron. Okay, so how many electron? 1 electron. Okay, for this reaction this one. So this is representing So this N is representing this electron, how many electrons are consuming in this reaction. Okay. Second is A. So A is nothing but electrode area, electrode surface area. Okay. So suppose your electrode is cylindrical, so you need to find out how much area is being used. Then D is for diffusion constant. Okay. C is concentration of in mole per centimeter cube. Then V is scan rate. Okay. Scan rate means how much voltage you are increasing per second. Okay. Suppose you are increasing only 0.5 volt per second. Okay. So your scan rate will be 0.5. Okay. And how you will be right? 0.5 volt per second. Okay. You are increasing this. So this is known as a scan rate. Okay. All other parameters are very simple. Okay. So by using this equation, okay, it can be derived that it is only 80 volt per second. Scan rate. Okay. Now, question number 6. In the cyclic, it is continuously, please keep posted. Okay, it is something which I don't know. In the cyclic voltagram given below for agriculture insecticide parathion, the cathode peak C appears. Okay, so see, this is the graph of cyclic voltammetry. Okay, this is the graph for cyclic voltammetry of parathion. Okay, and what are the reactions which are responsible for these peaks? Okay, if you know these peaks, then you will be able to understand. I will be able to understand to define this peak. Okay, so first of all, let me draw the structure of this molecule. Okay, one nitro group is there, then it is thiol, then it is arranged right here, C2H5O, and these are the two. Okay, so 2, 3, 4. So you can say these are the two molecules, so 2, 4, 5. Okay, so 5 valency of phosphorus is satisfied here. Okay, so this is the molecule which is known as parathion. Okay, so now what will happen if you are increasing current, potential. See, if you are increasing potential in x axis, okay, so it is negative potential. Okay, so at point A, okay, at point A, the nitro group of this compound will be sensitive. Okay, and it will the reaction will be happen like that. It is nitro NO2. Okay, remaining is whatever compound is this. Okay, it will gain 4 electron. Okay, because it is negatively, see, it is negatively you are adding negative potential, so you will get electron. Then potential same number of proton. Okay, it will give NHOH. Okay, plus H2. Okay. So see, means it is what is happening here. It is a reduction. Okay, so reduction, obviously above 0 it is cathodic, and below 0 it is anodic. Okay, so cathodic reaction is what happened at cathode? Cathode is connected with negative terminal, we know. Okay, and it will give electron, and if any ion is there like potassium, it will gain this electron and oxidize, reduce. Okay, so same thing is happen here, because it is A, so definitely A is nothing but reduction. Okay, so whatever peak above 0 is really it obviously it is a reduction. Okay, so here it is reduction happen. Okay, so after that this is the current is decreasing. Okay, and after that you are change the direction of your potential. Okay, now again you are applying potential in the opposite side. Okay, so this phenomena where NO2 converting in NaOH, this is not happening here. Okay, it is not happening here. So you can say this reaction is not reversible. Okay, so this reaction is not reversible, but as you are decreasing your potential more, you are changing your you are changing your potential in the opposite direction. At the point of B, a different reaction will be occur. Okay, so it is NaOH, it is already convert NO2 in NaOH. So this NaOH group again will be activate. Okay, and it will produce NO, nitroso. Okay, and it will give 2 hydrogen plus 2 electron. Okay, so what it is giving electron, so obviously it is oxidation. Okay, so this oxidation reaction is there. Okay, and it will happen at B point. Okay, this reaction is happening at A point, and this is a B point. Okay, finally, if you are again, okay, now it is NO group, nitroso group. Okay, so if you are again changing the direction of your potential, okay, so at C point, this point, what will happen? NO, it is already converted in NO, so this NO will be further reduced. Okay, because it is gaining electron, plus you can write here 2 proton. Okay, so it will gain electron, and finally it will convert in NH. Okay, so it is also reduction. Okay, so this is all about the cyclic voltammetry of this parathion. Okay, now you can easily answer the question. Okay, so cathodic peak C appears. Okay, cathodic peak C appears this thing. Okay, so this is the right answer. Nitroso is converting in. Okay, so where is, yeah, this is the right answer, I think. Oxidation of the nitroso compound to hydroxyl amine. Okay, hydroxyl means this is hydroxyl group and this is the amine group. Okay, NH. So that's why it is known, this group, whole group is known as hydroxyl amine. Okay, and why it is hydroxyl derivatives? Because this group is attached with this molecule. See, okay, this nitro is itself is converted in NaOH. Okay, so this group is attached here, and this nitro is not, now nitro is not there. That's why it is known as hydroxyl derivative of parathion. Okay, so see, oxidation of hydroxyl to nitro derivative. Okay, so it is happen here at B point. Then reduction of parathion to give hydroxyl derivative. Reduction of oxidation of sorry, it is oxidation, right? Reduction of parathion to give it is A point. Okay, so obviously C is right answer. C is for C. Okay, so this is clear. Any doubt? Up to here, any doubt? Okay, so this is the explanation. Okay, which I have already explained. The cathodic peak at C results from the oxidation of the nitro compound to hydroxylamine, as shown by equation. Okay, this nitroso group, it will get 2 electron, 2 proton, and convert in hydroxylamine group. Okay, so it is clear, I think. Okay, this question is also related from the previous question. Okay, in a cyclic voltammetry of agriculture insecticides parathion given below, the peak appear due to 4 electron reduction of the parathion. Okay, so 4 reduction real. Okay, first of all you need to find out how many reductions are there. Okay, so the graph is like that. Okay, so this graph is like that. Okay, so how much reduction are there? So I have already told you, na? Suppose this is the current and this is the potential. Okay, it is 0 here. So above 0 it is cathodic. So these 2 peaks are for reduction. Okay, so these 2 peaks are for reduction. You can say this is A peak, it was B peak, and it was C peak. Okay, so here NO2 gaining 4 electron. Okay, and converting energy. Okay, hydroxyl. But here this is only what's say here nitroso, which converted B. Okay, so nitroso so nitro so convert here getting 2 electron plus 2 proton and convert it to NH. Okay. So these both are reduction only, but because question is asking about the 4 electron reduction. Okay, so you need to check reaction, which reaction is occurring due to 4 electron. Okay, so obviously at point A, nitro compound gaining 4 electron, okay, 4 proton and converting it. So your right option will be A. Okay, so I think if you know this cyclovoltammetry and the reactions about this compound, then you can answer this both two questions correctly. Okay, you can say same answer. Okay, same question is, but the concept should be clear. Okay, okay, so this is all about question number 7. Now we need to find out, yes, why? Haha. See, that's why I explained like that, because reduction is happening, but here only 2 electrons are consuming. Na? What question is asking? How 4 electron reduction? Okay, so 4 electron reduction is taking place here only, right? Okay, that's why A is only right answer. Okay, so that's why I wrote this equation so you can understand properly. Okay. Then question number 8. The correct statement, it is statement. Okay, the correct statement, it is wrongly written. Okay, statement whatever it is statement only. Okay, among the following is the anodic striping method, the analyte is deposited by reduction, whereas in cathodic striping method the analyte is deposited by oxidation. Okay, so first of all, to answer this question, it should be clear in your mind what is the striping, okay, and how striping is work. Okay, so first of all I will explain about that, then I will go further. Okay, so what is the striping? If you see the graph, okay, and here suppose you are applying potential here and it is time. Okay, initially you are applying some potential. Okay, where deposition is going on, then you are decreasing the potential, so again it is coming in solution, striping is there. Okay, so you can say it is deposition, and then it is striping. Okay, if you are not able to understand by this graph, you can say simply, suppose it is copper electrode, copper electrode, okay, and suppose it is connected with negative terminal like that, okay, and it is in solution. Okay, it is solution of copper, Cu plus 2. Okay, so what will happen? The copper ion, because it is cathode, okay, it is cathode only, so cathode electron will flow like that, okay, and this two electron will react with copper ion, and copper metal will be deposited on this cathode. Okay, so this is the deposition up to here to here. Okay, so you are applying some potential where deposition is going on. After that you applied reverse potential. Okay, suppose it is changed plus and it is minus. Okay, so what will happen now? Because you are applying reverse potential, so the reverse reaction will be occur. Okay, so now the copper which was deposited in our previous case while deposition, now it will be stripe off, means it will be removed from your electrode. Okay, so finally it will be strip off with time. Okay, so this is the basic thing about the striping. Okay, so so here what so initially deposition is there. Okay, so here I also changed the terminal. Okay, initially it was negative. Okay, while deposition, but when it is striping it is positive. Okay, so when it was negative, okay, it is cathode, and when it is positive it will be anode. Okay, so while deposition of metal it was cathode, but while striping it is anode. Okay, so we will take this only as a anodic striping. Okay, but anodic striping, when deposition will occur, it was cathode. Okay, so this is the concept, it should be in your mind. Okay, so see, in anodic striping, so this is the anodic striping. Okay, because striping is when striping is happening, when you are connecting your this electrode with positive terminal. Okay, you can say anode. Okay, so this is the anodic striping method. The analyte is deposited by reduction. Okay, in anodic striping the analyte is deposited by reduction, obviously. Okay, by cathode, when it was cathode, reduction happened here because copper +2 ion converted in copper. Okay, so reduction occurred. Okay, so reduction. Okay, so up to here it is correct. Whereas in cathode striping the analyte is deposited by oxygen. Okay, so it should be reverse. Okay, so this option should be right. We will check other option also. In both anodic striping method and cathodic striping method, the analyte is deposited by reduction. No, it is not. It is not possible. Okay, how we can do reduction if we are changing the terminal? Okay, it is not possible. When it is connected, when it is negative terminal, then only reduction is possible. Okay, if it is positive terminal, the reduction is not possible. So obviously this is the wrong option. In both anodic striping method and cathodic striping method, the analyte is deposited by oxidation, not by only reduction, as well as not by only oxidation. All analyte can be deposited. Okay, so this is also wrong. Then question number D. In anodic striping method, the analyte is deposited by oxidation, whereas see in anodic striping, so we explained here anodic striping only, the analyte is deposited by oxidation. No, analyte is deposited by reduction. Okay, so it is wrong here. Whereas in cathodic striping, by reduction. No, it is also okay. So it is also wrong. So A is correct. Okay, clear this question? Understood how it is happening? Okay, good. Okay. So now I am moving. This expression I will just read out. In anodic striping method, the working electrode behaves as cathode. See, working electrode. Okay, working electrode means what? When you are depositing the material. Okay, so then it was connected with negative electrode. Okay, that's why it will behave as a cathode during the deposition step. Okay, during the deposition step it was cathode, and as anode during the striping method. Okay, just it is changed. Initially it was cathode, but while okay, so this concept should be clear in your mind, that it was while deposition it was cathode, and while stripping it was anode. Okay, so never confuse about this thing. Okay, so these are the two links point. With the analyte being oxidized back to its original state. Okay, initially it was reduced, but after that it is back reduced, oxidized. Okay, so first reduction at cathode, then it is oxidation at anode. In the cathodic striping method, the working electrode behaves as a anode during the deposition step and as a cathode during the striping. Okay, just reverse. In anodic striping method, the analyte is deposited by reduction and then analyte by oxidation from the small volume mercury drop. Okay, whatever, it is not important. In cathodic striping method, the analyte is electrolyte into small volume of mercury. Okay, we will also discuss about what is the mercury electrode now. Okay, I have made one slide here. Okay, so this is all about this question number 7. Okay, sorry, question number 8. Now it is question number 9. The difference in current per pulse is recorded as a function for the linearly increasing excitation voltage in case of, okay, see, difference in current per pulse, okay, difference in current, okay, difference in current per pulse means you are changing pulse, okay, and you are going to measure how much current is changing, okay. So it is already explained, it is a differential pulse voltammetry, okay. So differential pulse voltammetry means what, you are changing the pulse, okay, and you are measuring the current, okay. So if you plot the graph between current and voltage, you will get peak at particular when reaction is happening, okay, you will get peak, and by this way you can it is, this technique is more sensitive, so you can identify particular voltage where this reaction is happening, okay, very accurate. You can say E half, okay, so E half and E0 you can measure with this technique very accurate, okay. So it is explanation in differential pulse voltammetry, the difference in current per pulse is recorded as a function of linearly increasing excitation voltage, okay. You means see, it is linearly increasing excitation voltage and you are also giving pulse voltage, okay. So again I will okay, it is not symmetrical adjustment. Okay, so means we had, there are 2 points, okay, which we need to explain. What are difference curve is a constructive, sorry, linearly increasing, okay, linearly increasing, it should be like that, okay. This is the linearly increasing only, but you can say this is the E with respect to time, but you are also giving pulse, okay. So it will be like that, particular time giving pulse, okay. Now if you continue the graph, it is like that. Understood how I clubbed these two things and made this graph for the differential pulse voltammeter, okay. So let me check if something is remained. Okay, I think it is clear, okay. So a differential curve result consisting of peak, okay, then you need to measure, again you need to measure what, you need to measure current with respect of pulses, okay. So you will get peak, suppose you are getting sharp peak like that, okay. So this the directly proportional to concentration, okay, what, height, okay. So height of this peak means what, how much current is flowing, okay. So this means current is flowing more means concentration is more, obviously. Suppose you have in simple language you can say you have a NaCl solution, okay, and you are applying 2 electrode, okay, and you are able to flowing current. If you increase the concentration of NaCl, obviously current will flow more because more ions are there, numbers of ion will be increased, so it will be increased current. So same principle is there, okay. If current is more, it means your analyte is more, your analyte might be NaCl, AgCl, whatever, okay. So if it is there, it is more, the height of this peak will be increased, or in simple language we can say current will be increased, okay. So as current will be increased, the height of this peak will be increased, okay. So you can correlate this thing, okay. For a reversible reaction, the peak potential is approximately equal to the standard potential for the half reaction, okay. So you can say by here you can measure this standard potential for the half reaction, okay, whatever half reaction like Ag plus 2Ag, okay. If you are going to measure this thing, okay, what is the reaction potential of this thing, okay. So you can measure by this differential pulse voltammeter, okay. Clear this thing, okay. Then yes, yeah, okay, good. Okay, now finally question number 10. It is already memory based question, okay. the detection limit of differential pulse voltammetry is in range of, okay. So differential pulse voltammetry range, I think it is 10 to the minus 7 to 10 to the minus 8, okay. So it is already, it should be kept in your mind, okay, what are the range of this. It is nothing to explain, okay, but I need to explain something, okay. As an analytical chemist, you should know about that which analytical technique you are going to select to measure the analytic concentration, okay, because each and every instrument is not correct choice to measure the concentration of analyte, okay, because if you have means suppose 80% or 90%, okay, this type of concentration, okay, suppose you have copper solution which has 80% concentration, okay, it is very high, so you cannot measure by simple techniques, okay. So for this technique you need to measure what's a classical analysis, okay, volumetric analysis, titration, okay, because the concentration is very high. Suppose so you can say, sir, I can dilute it, I can dilute this solution, then I can measure by spectroscopy, okay, but it will not give accurate result, okay, because while you are diluting you need to dilute very high magnitude, okay, because spectroscopy like atomic absorption spectroscopy and ICP, okay, inductive coupled plasma, whatever, many techniques are there which measure in ppm and ppb, parts per million and parts per billion. So you need to convert your 80% conversion in parts per billion and parts per million. So you need to dilute it like 10,000 or 10,000 type like that, okay. So you require this type of dilution, okay. So while making this type this amount of dilution, you need to dilute again and again, okay. So if you are doing minute mistake, okay, you will not able to identify, okay, it is human being mistake and it is obviously there, okay. So it will be multiplied by 10,000 times, okay, means if your instrument is itself is reading it is giving wrong reading, suppose it is only giving 10 ppm high or less, okay, so it is very it is acceptable for this instrument, okay, but when it will be multiplied by your dilution which is 10,000 times, okay, so it will be means you can, okay, means 1 lakh time, okay, so 1 lakh time ppm concentration is changed, okay, so your spectroscopy will not give correctly, so you need to go with classical analysis only, which is titration, okay. So or you can say volumetric analysis, titration volumetric, okay. So it should be clear that what is the concentration of my analyte, okay. If concentration is very low, suppose we already discussed that if concentration is range in -3, okay, to 10 to the -5, okay, if this range is there, then you can measure by spectroscopy like UV, visible, okay, you can go with this technique. If it is more or less like 10 to the -5 to 10 to the -7, then you can go for fluorescence, okay, it is also very sensitive technique. If it is further decreasing, means 10 to the -7 to 10 to the -8, which is very less, okay, then you can go for voltammetric, okay. So it should be clear in your mind when you will go for voltammetry when your concentration is very low, okay, your analyte concentration is very low, then it is very wise, means wisely how you will select analytical technique wisely, okay. So it will be based on your analyte concentration also, okay. So this is the explanation of this question. Generally, detection limit with differential pulse voltammetry are 2 to 3 order of magnitude lower than the classical voltammetry, okay, lies in the range of 10 power -7 to 10 power -7, okay. It should be keep in your mind. If you work in a analytical field, then it will be very helpful to identify this thing, okay. So I just want one more explanation about the doping marking electrode, okay, because I think it is not clear, okay, in this this class. Okay, so how dropping mercury electrode works. So first of all, if you remember this name, means dropping mercury electrode. Okay, so means it is saying that mercury is dropping. Okay, so how it is happen? See, this is the mercury reservoir. Okay, where you fill mercury. Then it is connected with this tube, and this tube is finally connected with this capillary. Okay, so this is the capillary. So when you open this clamp, okay, the mercury will come down. Okay, and by this capillary, which is very small aperture, okay, very small dia, so the dropping, it will one drop will be generated here. Okay, one drop will be generated. Okay, and it will be, and then you will apply potential here. Okay, so it will be work as a working electrode. Okay, so after approx 3 to 5 seconds, okay, after 3 to 5 seconds, this drop will be fall in the solution, then again new drop will be generated. Okay, so what is the advantage of this technique is it will give continuously new electrode surface. Okay, so it will give good result. Okay, because it will be not contaminated by the solution, and it will be smooth, it will give smooth surface, and also the area of surface you can measure. Okay, area of the surface you can measure according to the weight of this mercury drop which is falling, okay, continuously. So by this way you can use this mercury dropping electrode. Okay, so this is all about this assignment. Okay, I think it is clear. Any doubt you can ask, any doubt from this assignment, or if you have any doubt, means doubt from your class, or what say, means your lectures of this week. If you do not have any doubt, then we will take 5 minutes, okay, break, and then we will start again. Okay, 5 minute break I will take, then we will start. Okay, so we should start now. Okay, so this chart is representing all about electrochemical methods which are being used in electrochemistry. Okay, so it might be static method where I is equal to 0, okay, and dynamic method where I is equal to not 0. Okay, so it is a potentiometry, okay, where I is not changed, only potentio you measure by potentiometry. Okay, then it is dynamic method which is control potential and control current. Okay, obviously name says control potential and control current. Then variable potential. Okay, so here in voltammetry what we are doing, we are changing potential and we are observing current. Okay, so it is known as voltammetry. Then uh, stirred solution, so it is stripping voltammetry. Okay, or quiescent solution. Okay, so in stir, if your solution is being stirred, it is known as hydrodynamic voltammetry, and if it is stagnant, then it is known as polarography and stationary electrovoltammetry, polarography and voltammetry, and cyclic voltammetry. So this is the tree where you can understand how different type of voltammetry are there and how it is described. Okay. Now we will discuss about voltammetry. So voltammetry, from the discovery of polarography in 1922 by the chemist Jaroslav Hairovsky, received the Nobel Prize. Okay, so he received Nobel Prize because these techniques are very innovative and it is being used in very important and significant applications. The earlier voltammetric method experienced a number of difficulty, but after 1960s and 70s, a significant advantage were made in all area of voltammetry. Okay, so theory is clear, then methodology, instrumentation is also improved. Okay, which enhance the sensitivity of analytical method. Okay, so nowadays we are using very sensitive and very advanced instrument which are being used for the voltammeter. The common characteristic of all voltammetric techniques in that they involve. Okay, so these are the common characteristic. The application of potential to an electrode. Okay, so what potential you are applying. So on the basis of potential, how much current is flowing. Okay, in electrochemical cell. In many cases, the applied potential is varied for the current is monitored over a period of time. Okay, so what we are measuring current as the function of applied potential. Thus all voltammetric techniques can be described in some function of E, I and T. Okay, E means potential, I means current, and T for time. Okay, so the governing law is only Ohm's law. V is equal to I. Then how it is work, a voltammetric cell. Okay, so this is the basic about the voltammetric cell, how it look like, as we have already explained, but little bit we will explain here. Okay, so 3 electrode, working electrode, auxiliary electrode and reference electrode. 3 electrodes are there. In between these 2 electrode we measure voltage, it will remain constant. Okay, and these 2 electrode current will be flow. Okay, so this is the complete circuit. Okay, and this is all about the cell. Okay, I think we have already explained it very clearly. Then what is the working electrode? The working electrode are the various geometry and materials ranging from small AG drop to platinum disc. Okay, it is either we have already discussed now, mercury dropping electrode. So it is used mercury dropping electrode or platinum disc, platinum wire, whatever. Okay, so these are the working electrode. So mercury is displayed a wide negative potential range because it is difficult to reduce hydrogen ion or water at the mercury surface. its surface is readily regenerated. Okay, why it is regenerating? Because it is dropping mercury level. Okay, so after 3 to 5 seconds, drop will be fall down and new drop will be generated. By producing new drop or film, and many metals ion can be reversibly reduced into it. Okay, so by this way your mercury is creating an electrode, and on the this electrode many ions can be reduced, not oxidized, it is reduced. Okay, other commonly used electrolyte metal are gold, platinum and glassy carbon. Okay, then we will discuss about the auxiliary electrode, or it is also known as a counter electrode. Okay, so passes all the current needed to balance the current observed at the working electrode. Okay, so some current will be obviously required, which will be flow in the electrochemical cell, and finally your reaction will be occur. Okay, so this because we already know that in the reference electrode negligible current is flowing. Okay, you can say zero. Okay, zero current is flowing there, so that's why the current is flowing between working electrode and auxiliary electrode. The reference electrode, and then what is the reference electrode? The reference electrode should provide a reversible half reaction. Okay, reversible half reaction means the reaction should be reversible. That's why it can be regenerated. Okay, Nernstian behavior. Okay, it's also should be follow the Nernstian behavior. It's its only role into act as a reference is meaning and controlling the working electrode potential. Okay, V or E, it is measured potential. The most commonly used reference electrode for the aqueous solution is calomel electrode. Okay, so this is all about that. Okay, it is like that. So what is meaning of this thing is Ag is convert, and it is, you can say, some chloride solution. Okay, so Ag is converting in Ag plus 2 by reacting chloride, and again it can convert in mercury. Okay, so it should be reversible like that. Okay, this instrumentation we have already discussed. So it is okay, it is working electrode. It is not clearly observing. I will write down. Okay, then it is counter electron, this thing, and it is reference electron. Okay, so working electrode, reference electron, counter electron. Okay, these all are connected, and like that it is not clearly written. We have already discussed about this, so don't worry about it. Someone wrote, okay, then the minimum potential required to initiate the electrolysis process is called decomposition potential. Okay, the minimum potential required to initiate the electrolysis. Okay, so whatever electrolysis will happen, you require some potential. Okay, and it is depend on your analyte. Okay, which ions are there in your analyte. Okay, so it is known as the decomposition potential. The Faraday current is the current generated by the reduction or oxidation of the chemical substance of your electrolyte. Okay, so it is also it will be also depend on your electrolyte. Okay, so means how much current is generating due to what? Due to reduction or oxidation of ion. Okay, so metal is somewhat oxidizing. So this metal, it is if it is zinc, then potential will be different. If it is you can say gold, then it will be different. Okay, so different type of potential you need to apply. Okay, so it is known as a differential decomposition potential. Okay, and how much current you are required. So capacitive current, also called as non-Faraday or double layer current, does not involve any chemical reaction. It only causes accumulation or removal of electric charge on electrode, and it is electrolyte solution. Okay, so some current will consume to make a layer. Okay, you no need to worry about going deep about what is happening. Okay, so it is only means what it is doing, it is accumulating the charge. okay, or sometimes it will remove the charge. Okay, so some current is consumed in this way, so it is known as a capacitive current. Then the limiting current, the electrochemistry in the limiting value of Faraday current that is approached is the rate of charge transfer. Okay, just a minute. That is approached is the rate of charge transfer to the electrode is increased the limiting current can be approached. For example, by increasing the electric potential or decreasing the rate of mass transfer to the electrode. Okay, so limiting current means you can a certain point the current will be limited. After that, you will not able to you increase potential, but the current will not increase. Okay, this point is also discussed in last week. Okay, how you are applying voltage like that, you are applying voltage, so current should also increase, but after some time it will not increase. Okay, so it is known as a limited current. Okay, so these things are already discussed. This is our not in your syllabus. Okay, yeah, this is the typical curve of cyclic voltagram. So it is again plot in y-axis it is current, and in x-axis it is potential. Okay, so when you are increasing potential, okay, here current is almost constant, then current is increasing suddenly here at this peak, then it is decreasing. Okay, so why it is happening like that? Okay, so two type of reaction are happening there. One is reduction and another is oxidation. Okay, so this is the 0 point. Okay, above 0 it is a cathodic, so it will be reduction, and here it is anodic, so it will be oxidation. Okay, so here at that point oxidation is occurring. Okay, so when oxidation will be occur, current will be flow. Okay, and this current, the flowing current you can measure by this IPA. Okay, yeah, it is a draw reversely. Okay, cathode it is reversely, but you can understand. Okay, so it will be negative. Cathode means negative. Okay, so it will be, if you are writing like, it will be negative and it will be positive. Okay, so don't go with these signs. Okay, I have changed this. Okay, so it is a, you can say IPC and IPA. Okay, so this IPC you can measure and this potential you can measure. Then if you change the direction of potential, then again here suppose it is a redox reaction. Okay, so redox reaction means what? AM is converting, reduction is there, so AM, you can say AM plus, taking one electron and converting in M, then again it is AM minus losing electron. Okay, and converting in M plus. Okay, so suppose this redox reaction is happening, so here it is at cathode, reduction is happening, and here it is oxidation is happening. So this IPC and IPA is if it is same, then you can say it is reversible reaction. Okay, here also you will get some difference. Okay, IP and IPC, so delta E will be also you can measure. Okay, and it is fixed for reversible reaction. Okay, so just a minute. Okay, so it is all about this thing. This is the theory. The applied potential control the concentration of the redox species in the electrode surface. Okay, so current potential applied potential control the concentration of the redox species at the electrode potential is described by Nernst equation. So these are the concentration, okay, reduction and oxidation. Okay, so these all are constant, and I think it is already discussed. Okay, so this delta P, what is the delta P? It is a difference between potential of anode, you can say anodic potential and cathodic potential. Okay, where the oxidation and reduction occur. Okay, so the difference between this potential is equal to, you can write this whole thing, or simply we can write 0.0. I think it is 592 divided by n. Okay, if you calculate this all things, okay, R T is 25 degrees centigrade, Faraday 96,500. If you put all this value, you will get, yeah, it is written here. Okay, so you will get this value. Okay, and it is about 60. If it is about 60 milliwatt, okay, then you can say the reaction is let's say reversible. You can also calculate E0, okay, EPC plus EPA divided by this, you can say average, okay, average of these two potential are EPA. Okay. Then again this Randless-Sedgwick equation, okay, Randless-Sedgwick equation, where you can say IP is what? Current is flowing with scan rate. Okay, so it this equation representing that your current is proportional to scan rate. Okay, current is proportional to scan rate. Okay, so if you increase the potential rate, scan rate, okay, then your current will be increased. Okay, so suppose you are plotting graph like that. Suppose it is, okay, suppose this is for I1, V1, scan rate V1. If you are increasing scan rate, then I will be also increased. So what will happen? It will be like that. Okay, it is not very symmetrical, but you can understand. Okay, so it is V2. So obviously V2 is greater than V1. Okay, then you will get this type of graph. Okay, so this is typical car. It is made at efficiency 6. Okay, you are going to measure efficiency 6 in presence of KCl. KCl is your supporting electrolyte. Okay, so you will get this type of cyclovoltammetry. Okay, so it will be sometime, means it is depend on how you are plotting your graph. Okay, because it is negative here, so obviously it is negative, so it will be reduction will be here. Okay, and oxidation will be right. Okay, so it is also depend on how you are plotting the graph. Then what is the irreversible oxidation or reduction? Okay, so activated over potential, extra energy applied to the electrode in the form of increasing potential. Okay, so it will be promote irreversible oxidation and reduction. Then reversibility depend on the relative values of electron transfer constant, the change of the potential scan rate. Okay, it is already discussed. If the ratio of K, S and N is small, then Nernstian concentration cannot be maintained. Then the process is called quasi-reversible. Okay, so these all parameters should be keep in mind, that how you can control. But you don't need to worry about this so deep. Okay, so application CV is rarely used in CV is rarely used in quantitative determination, but it is widely used for qualitative. The study of redox process, okay, you can study redox process very well. For understanding the reaction of intermediates, okay, so if intermediates are forming, okay, so according to their oxidation state, okay, current will be different. So you can measure that which oxidation state are there. Sorry. So on the basis of that, you can explain that what is the mechanism of this reaction and all. Okay, for obtaining stability of reaction. Okay, so it is very deep. Okay, so it is all about this week class. Okay, student. So we have discussed about week 11 assignment and concept which are taught in week 11. Okay. So I think it is done. Okay. And if you have any question, any doubt, you can ask. Okay. I think I have done from my side. All concepts and all things are discussed already. So I will explain one more thing. Okay. So how the isomers will be represented in cyclic voltameter. Okay. So the isomer will be represented like that. Okay. So suppose this is for mer and this for okay. So what is meant by mer and phase isomers? Okay. So phase means one phase is same. Like if you are drawing this type of molecule. Okay. So one phase is same. Suppose I am taking ligand LLL and here X. Okay. So you can say these are the two phases. Okay. One phase is this one, another this one. So this is the phase isomer. Okay. Where M is a little bit different. Okay. Here you can say it is X. Okay. It will be like that. So you can say at particular potential mer will be reduced. Okay. And after you increase little potential, you will increase potential little bit more. The phase will be the phase isomer will be reduced. Okay. So you can find out delta E and you can characterize further. Okay. To understand about the phase and isomers. And so these techniques, let me erase it. Okay. So these techniques are also used in biological study, where very minute sensitivity, very high sensitivity and very minute concentration need to measure. Okay. So generally here we used one electrode. Okay, you can say working electrode. So it will provide electron. Okay, and it is coated with some mediator. Okay, so it is coated with some mediator. So it is MO, mediator oxidation. Okay. It will gain electron from here and it will be reduced MR. Okay, mediator reduced. Okay, so it is getting electron from the surface and it is coated on surface only, surface of electrode. Okay, so it is gaining electron from electrode and being reduced. It is M for mediator. Okay, then it can give it can give electron to enzyme, and enzyme will be reduced. Okay, from here to here, enzyme will be reduced. Okay, so now this reduced enzyme again give its electron. Okay, and it will be oxidized. Okay, so what will be oxidized? Your substance. Okay, so it is reduced ER getting EU. Okay, so enzyme is oxidizing, so your substance will be reduced and it will make product. Okay, so like that it will be work, and it is a different layer of modified electrode. Okay, so it is known as the surface modification. Okay, so it will improve the sensitivity of your electrode. Okay, and stepping method we have already discussed. Okay, anodic and cathodic we have already discussed, I think, so it is no need to explain again. Okay, so this is all about this week class. Okay, we will meet in next class. Bye.